So I work at a company called App Dynamics, and we just briefly work on, we have a product that does production level monitoring and troubleshooting of like mission critical business apps, and that's why there's a picture of superhero there, because our customers consider us superheroes. We're working on a PHP version of our product right now, which is a PHP extension you drop into production environment, and it starts collecting, analyzing a source of data about your app and helping you instrument and troubleshoot and get to the root cause of the problems really quickly. So if you're interested in that, come talk to me afterwards. But we're not here to talk about that. We're here to talk about math. So these slides will contain some math, but don't be afraid of it because it's awesome math. It lets you do some really cool stuff. This is my Twitter handle, for those of you who don't know already. And this is both a very cool and very horrible thing. I got it in October 2008. I used to have a different one before, but then through various shenanigans, I was able to acquire this one. And I didn't have the foresight to see what was going to come next. And I know a bunch of other single-letter Twitter people, one of whom is here, Helgi, if you know him, he is at H. But I know a bunch of others. And so the advantages of having a single Twitter handle is fame, apparently. People like to do all sorts of profiles on single-letter Twitter handles, like from A to Z. The Atlantic did that. Wall Street Journal came and did an article and like photographs and stuff like that. I'm like, what, Wall Street Journal is interested in this stuff? Seriously? Followers. I have like 54,000 followers right now. I have no idea who they are. I mean, I know like a couple of hundred maybe, but that's it. But another advantage is maximum reply space, right? 140 characters minus the length of @ A and space. It gives friends and other people 137 to reply back to me. I feel like I'm doing them a favor. The cons are, this is what my reply stream looks like most of the time. It's just full of garbage. And if you look at the times here, they are all very closely spaced together, so it's pretty much impossible to filter anything visually. And I thought for a while about how to solve this thing, and it's like, well, maybe I'll write some sort of list of rules by which to reject or accept some of these and so on, but it's really hard to do. Any sort of hard-coded system is not going to be able to adapt. So I decided to use machine learning because I'm interested in that stuff, and the best way to learn something is to apply it and do some sort of hack. So after I wrote this little tool called Reply Cleaner, this may not look that much different to you, but in my estimate, it's like 80% better already. First of all, because they're much less closely spaced together. So I can actually visually filter through them, just scroll on my phone and so on. And the actual quality is improved. And the way this thing works is that it uses a trained model based on a number of tweets that I've collected to classify them into good and bad ones. And for bad ones, it just blocks the users. They like disappear from my view completely. And that's because Twitter doesn't really give you a way to individually like exclude single tweets from your reply stream. And so it looks much cleaner. Like this is an example on my phone where somebody replied to me and I was actually able to look at it even though I don't follow them and have a conversation with the person. But if you look at this, like there's still some, even though it's readable, but it's still some junk there. I don't know why people use @A in very random ways. And then I can, you know, filter through and find stuff like that. People don't believe that you know, single letters exist. Or this stuff. How can people like @A and Dick C, who is the CEO of Twitter, only have 1 million or less followers? So conclusion, I still hate humanity, just a little bit less. So machine learning. Machine learning is a branch of artificial intelligence. There's no really widely accepted definition of what it is, but I kind of like this one, which was given by Arthur Samuel in 1959. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. They learn based on the data that you feed them, based on the experience, so to say. And it's used in a variety of different industries, and especially the proliferation of data-based, like big data and data-driven analytics and everything like that, for things like spam filtering, which is very helpful because nobody wants to read spams. This is like just a screenshot of what ends up in my spam folder. I'm very thankful to Gmail for that. Things like recommendations based on what you buy and what merchants like Amazon think you will want to buy based on your patterns. Machine translation. Google Translate is actually uses statistical machine translation. It's not rule-based or example-based. So they have a big body of examples of source language and the target language, and then do a whole bunch of analysis and machine learning on that in order to use whatever 58 languages that they support right now. Things like clustering. This is Google News example where it looks at the incoming news stories and then figures out what topics they belong to automatically, and then clusters them around those topics. So this is all like very cool stuff and related to big data. And one of the fundamental things to understand machine learning is that it's based on the concept of features. And a feature is an individual property of something that you are observing or measuring. The really easy way to explain this is if you look at like a label, nutritional facts on some type of food, you can see things like, you know, fats, cholesterol, sodium, carbohydrates, and they all have numeric values next to them. You can think of these as features that describe that particular type of food. And if we take all of those and put them in an array, then we get what's called a feature vector. It's basically a set of features for a certain observation. So as an example, if we were trying to do a model that predicts house prices based on some parameters or features of the house, we may come up with things like, how many rooms does it have? What's the square footage of the house? How old is it? Does it have a yard? And so on. And for each one, when we have that feature vector, if we also derive some sort of weights that apply to each feature, so let's say these weights are price based on like $100,000. So if each room gives you approximately $102,000, increases the price of a house by that, or each year of the house age decreases by 10,000, and so on. So you take the features and the weights, but before you do that, there's one more thing that is usually done, is that you pad them. And you basically add one, prepend one to the feature vector, because that corresponds to this sort of offset weight. It's a starting weight. And then you use dot product to multiply them, and then you get your prediction. Now, here's where a little bit of math comes in. This is the first slide. For those of you who don't remember what the dot product is, it looks something like this, right? We have our input array of various features with the 1 in front, and theta usually denotes the weights for those features. They're also called parameters. And it's actually really easy. All it is you take the pairs of those, you multiply them together, and you add them. And that's it. That's a dot product. With me so far? Okay, good. I see nodding heads. Now, the goal of what you want to do is to take a body of some training data that you already have examples of. So things like, if you're trying to do spam filtering, there would be a whole bunch of emails, and then to sort of label that says whether it's a good or bad email. And you feed that into some sort of learning algorithm, and there are various types of learning algorithms. We'll mention just one in this one, like one of the simplest ones. But what comes out of a learning algorithm is what's called a hypothesis, or it's also called decision function sometimes. And the hypothesis represents what the system has learned so far. And then once you have your hypothesis, you can take it and apply it to new data and make predictions based on this trained model. If you feed it new data, you can classify it to, whatever number of categories you decide. So a hypothesis is usually written as a function h based with the input x and parameterized by this theta. So this is the input data. This is our feature vectors or training data. These are the parameters, those weights. And what comes out here is the prediction y. Now the task of our algorithm that we want to apply to this is to determine the best parameters to give us the best prediction. There are a couple of learning algorithms. This is probably the simplest one, called linear regression. And it applies when you have a relationship of some sort between one or more input variables and an output variable. And in the simplest case, you just have one input and one output. So in this case, let's say I have some sort of training data. I looked at my collection of whiskeys and so on, right? And I see, okay, on the horizontal, I'm going to have my whiskey age, which is the input. And on the vertical, I have a whiskey price in dollars. And so I just map them, and now I want to fit a line through this that fits it in the best way possible to minimize the errors. So if we fit the line, it might look something like this. And now that we have this line that has a certain slope, certain inclination, we can use it to make predictions about whiskeys I don't have yet. So for example, I don't have any data for 25-year-old whiskeys, right? But now that we have this line, we can trace it and see that it comes out to be about $140 or so. You know, it may not be entirely accurate, but this is what it is based on the data that I fed through this model. Now, the problem is that linear regression works pretty well for numeric cases where you have some sort of output like price or temperature or whatever, but it doesn't work very well when you want to classify things like into good or bad and so on. And the problem is that the output of linear regression, it's unbounded. It's just a domain of the whole, like, real numbers, right? What we want is just 0, 1 mostly. And you can threshold it, let's say, okay, if it's above 80, then I'm going to consider that good, or if it's below 80, I'm going to consider that bad, but it doesn't work very well in practice. So there's another algorithm called logistic regression. And it uses this special function called sigmoid function, or logistic function, because it looks sort of like letter S. And it's very useful for us because it transforms its input to be contained between 0 and 1. And so if you look at, like, its approaches 1, as the greater the z becomes, and approaches 0, the less the z becomes. And that way, once you apply some sort of input to this and get a number between 0 and 1, you can threshold it on whatever value you want. And in this case, what is z? That's just our dot product, that prediction that we were making. So if we just substitute that back in, this is our hypothesis. This is our decision function that we're going to use. And so if you want to think about it more intuitively, what it gives you is a probability that, let's say, y equals 1, so something is a good in our good class for a certain input x. And this is called logistic regression. So for example, if your hypothesis is this email spam or not, and it gives you 0.7 output, that means there's 70% chance that this is a spam. And it's up to you to decide, okay, what's my threshold? Is it 70%? Is it 50%? And so on, depending on how many false positives or negatives you want to exclude. So building the actual tool, what goes into that? Well, we want the training data, or what's called a corpus, that we want to train our algorithm on. And corpus is a collection of data used for training and testing the model as well. Since this is not big data, I don't need a whole lot of it. I don't need like millions and billions of various training examples. So what I did, I used a library called Firehose, which can be used to hook into Twitter's streaming API. And so I wrote a little thing that sat there and just downloaded my reply stream into MongoDB, which is really useful because it just works with JSON data, and Twitter sent me JSON data back. So I got about 8,500 tweets from my reply stream. Took a little bit of time, maybe a couple of weeks or so, because even with all the garbage that comes into it, it's not actually that prolific, right? So now that I had this, I needed to derive my features all my training points from that. And when you try to figure out what sort of features you can extract from your training data, you want to make them independent and discriminant. What do I mean by that? Well, independent means that feature A should not co-occur with feature B too frequently. It shouldn't be correlated with that. So, and discriminant means that each particular feature should give you some sort of valuable data about the whole observation. It should give you some uniquely classifiable thing. So, for example, if you decide to have a feature, make a feature out of the first letter of the tweet, like that's not actually discriminant because it doesn't give you, classifiable data. You can't say that just because the tweet starts with the letter B, it's going to be bad or good. You want to have something that actually helps you make a decision. Here are some of the possible features that I came up after sort of looking visually and analyzing which tweets were good, which were bad. I noticed that for the bad ones, a lot of times the @A was at the very end of the tweet, or if it was followed by 3 dots. Sometimes it was very short, or had a lot of user mentions in the tweet, a lot of hashtags. Language was very important, like what language tweet was written in, and a bunch of others that I'm not showing here. But these were my sort of sample space of features I wanted to consider. So once I had these, then I just wrote a little function that I give it the tweet, and it extracts this feature and gives it back some sort of numeric value. And you can pretty much transform anything into a number, right? Whether it's a Boolean or even a string, you can make a number out of it, and that's good. You usually want floating point values for this stuff. And then you take your corpus, you run it through all these extractors for features, and you get back a whole number of feature vectors. So basically, you have a big array of smaller arrays, one for each of the observations. So I had 8,500 of these for each tweet, and just save it to database. I mentioned language, and that was one of the most important features actually to get right, because for example, if I see that Indonesian or Tagalog language, it's probably garbage. I ran a little bit of just analysis on all the 8,500 tweets, and if you look at it, you'll see that Indonesian is like there are more tweets in that than in English, or like Somalian or Swahili. I guarantee you, nobody's really tweeting at me in Swahili or Somalian. Like nobody's actually saying, hey, @A, blah, 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 blah. So I needed, like this was useful data to use in classifying tweets. Now, Twitter doesn't really give you a way to know what language the tweet is written in, so you have to do some sort of language detection. You can't trust the language field in the user's profile. There's a field that says like what language they speak or whatever, which country they're from, because there's many examples where it was just said English and they were actually using Indonesian or something. So you have to use tools like in Pair there's text language detect, or in Peckle there's a new extension called TextCat, which uses trigram analysis and tries to figure out with some probability what language a certain piece of text is written in. And this took a little bit of time to get right because it's not certain that this is the right language. And sometimes it just says, oh, I give up, I don't know what this is, and then you have to make some sort of decision based on that. But once I got through that, then I actually had to do this manual classification. I had to go through pretty much all of those tweets and say, are these good or bad? Well, thankfully, only a certain number of them, a small number, were good. So I wrote this little tool using Twitter, what's called Bootstrap? Yeah, which lets people like me who don't want to do any sort of visual design to just make something work. So this just throws up tweets from the database, and I can quickly scan and see, okay, this is actually a good one. This beer in Norway tweeted me saying, hey, are you visiting any of the Trappist breweries, monasteries? And I'm like, okay, this is a good one. Go to the next page, and so on. So this was tedious work for about, I don't know, several hours. But once I was done with this, I had my inputs, which were the feature vectors that I extracted from the training data, and I had my labels. Are they good or bad? That's my output. Now that I had this, I was almost ready. And I say almost because there is a fairly big problem with the training data that I collected. And that's, the problem is that it was very biased. The number of the bad tweets far outweighed the number of the good ones. It was like 1 or 2% only were good and the rest were bad. So if you just fed this into the learning algorithm as is, it would actually not give you very good outputs because it's so biased. So we need to adjust this bias so that they're approximately equal. Now, there are two ways of doing that. One is called oversampling, and this is where you take the smaller subset and you multiply it, you make multiple copies of it until it's about equal in size to the other class. The problem with this is that the bias was so high that if I took those 100 or 200 tweets or whatever and just copy them around, that it would also not give you a whole lot of good data. It wouldn't contribute a lot of variance to the classes. And the other one is called undersampling. And this is sort of the opposite. You look at the large class and you drop most of that data so that the remainder is kind of equal to the other class. The problem with this is that if I did that, my total corpus would end up being like 300 or 400 tweets, and that's not small data, that's tiny data. Okay. So a solution was to use something called synthetic oversampling. And this is where instead of just blindly taking the small class and multiplying it, I synthesize, like I basically make up feature vectors by sort of predicting what constitutes a good tweet, right? So I can, with some variances, some randomness thrown in. So I can say like, oh, 90% of the time, a good tweet will be in one of these languages that I understand. Or it's 2% of the time, the good tweet actually does have @a at the end, and so on. And so I make up these feature vectors and add them to my good class. And that way I have enough variance to help the learning algorithm. So now that we have the inputs, the outputs, and the bias correction is done, they're approximately equal in size, we need to actually train the model. So how do we actually determine these weights for each feature? Well, the first thing we need to look at is something called a cost function. And this measures how far the prediction of the system is from reality. So it'll give you some sort of output, and then you need to measure how far does it actually correspond to what you fed it in the first place. And the cost depends on the parameters of your model. The less the cost, the closer we are to the ideal parameters. More math. This is just sort of an illustration that says the cost function, you give it the hypothesis, what the model has learned, and the actual data, which is y, the labels, and you just go through all your training examples and sum them up and average them out, and that's your cost, averaged all the training examples. And for logistic function, the cost turns out to be something like this. If the class is 0, then it's that function, and if the class is 1, it's that function. Question, like, why is it specifically this? Well, if you graph them out, they'll look something like this. And the idea here is that if for the correct guess, when the system guesses correctly, the cost should be 0. But when it guesses incorrectly, the cost should be huge. And these functions, if you look at them, if the correct prediction is 0 and it guesses correctly, cost is 0. But if it guesses incorrectly, that's like asymptotically infinity, basically. It's a huge cost. So we penalize it for incorrect guesses. Same for the other example, but inverted. So the goal of our algorithm is to minimize this cost. over these parameters or weights. We want to find the best values of theta that minimize this cost. And the algorithm that is one of the simpler ones to use is called gradient descent. And to think about it intuitively, imagine you have like a hilly surface of some sort. And you're standing at a certain point of that surface and you want to get down to the lowest point. So what you do is you sort of look around and find the steepest decline and you take a step in that direction. And then you repeat that. You look around again and you're like, okay, so this is the steeper direction now. You take another step. And eventually, if you repeat it enough times, you'll end up at some low point. And I'm not saying you'll end up at the lowest point because it's not a global minimum necessarily, but you'll end up at a lowest point possible for your starting point. Notice that in this example, we have two different starting points and they lead us to two different minimums, and that's okay. I mean, there's not much we can do here with this specific algorithm, but it is one of the simplest ones to explain. And the general equation for how this algorithm works is something like this, which I'll explain in pieces. So these are the parameters. Each parameter, depending on how many features we have, we update it. This is the learning rate for our system, and this controls how big of a step to take. You can take a big step, you can take a small step. And if the learning rate is big, you have aggressive descent, but you may sort of overshoot the minimum and end up kind of bouncing back and forth or even like out of the valley completely. And if it's too small, it might take too long because you have tiny steps. You take tiny steps and you have to do 100,000 or more. And this is just says this is the slope, this is the incline or decline if you want of at the current point for this particular feature. So this is our slope. How steep it is and in what direction. So you basically take this and you keep doing this for a number of iterations or until your cost difference for each step is below a threshold of some sort. So it converges. Another way to sort of monitor your progress is you graph out your cost function, and if it starts approaching zero, then you know you're going in the right direction. So this is the final update algorithm, right? It looks kind of complicated, but this is it for the logistic function. We basically, for each parameter, we subtract this learning rate multiplied by this number, which is basically our cost, our slope that we calculate over all the training samples. And so let's just take a quick example. Let's say we only have one feature. So and we only have two samples in our set. So we have one with number 12 and -3.5, and we pad those with ones at the beginning, right? And the first one we'll consider good, and the other one we'll consider bad. So, and we'll just randomly start with weights being 0.1 and 0.1 for each one. And let's say learning rate is 0.05, right? So we calculate the hypothesis for the first one. That's that sigmoid logistic function. We do the dot product and then put it in, and it comes out to be like 0.786. And this is for the second sample, 0.438. And this is our temporary value that we're going to save the calculation into, because we don't want to update our theta array yet, because we're still using it in calculating the hypothesis. So that's that previous slide's example equation, just with substituted stuff in. So our current one minus 0.05, which is the learning rate, and then this is the sum over both of the ones. And if you just plug the numbers in, it comes out to be 0.088. That's our next iteration for the first parameter. And for the second one, it's 0.305. So now that we have those, we plug them back into our theta array and keep going. So instead of 0.1, 0.1, now we have these values. And if you keep doing it long enough, eventually you'll get to the right answer. For logistic regression, it's pretty much guaranteed that you'll get to the minimum. So somebody asked, when I gave this talk the first time, somebody asked for a sample code. They wanted to see sample code. I'm like, okay, let's do sample code. So can everybody see that? Or larger font? All right. So let's say we have 3 features, and my data set is like, I want to live somewhere around the world where average winter temperature is not too low, where city population is fairly big. I like big cities, and it has an airport I can fly to from USA directly. So I kind of went through several cities I had in mind, collected data for them. Like the first column shows the average winter temperature in Celsius. The second one is population in millions. And the third column is, does it have that airport or not? Those are my feature vectors. And I also labeled them. Do I want to live there or not? So I have 0 and 1. And I'm just using floating point numbers for everything because it simplifies stuff. And then I have this hypothesis function that just calculates a dot product and plugs it into that equation, and that gives you back that output between 0 and 1. So what do we do here? I initialize the weights, just random starting parameters. And then my learning rate is 0.05, and I'm going to take about 20,000 iteration of this to see where we get. And this is the guts of it, which I'm not going to look at it too closely. It was basically the same idea. You go through all your parameters, and then through all the samples, you calculate the hypothesis and update the parameter, just like on the slide. I link to this at the end in the resources, so you can check it out to your heart's content. But then we have our weights determined, and we can do predictions. So we can test our model, feed it some new data, and see what it outputs. And so if I run this, it works for a little bit, and then it gives me something like this. So 20,000 steps. These are the weights that I determined. And now I want to validate it, right? I want to go through my training data that I fed it and see if it tries to predict, do prediction, does it actually correspond to the manual labels I gave it. And in this case, it predicted fairly well, but it missed too. So my correctness is 80% for these weights, which is not too bad. And then I can test the model. I can feed it some new data saying like, okay, well, what if there's a city that's about 0 degrees in the winter on average, and it's a 1.1 million, and there's an airport that I can fly to from USA directly. And it says, yeah, you want to live there. Well, what if there's one that's minus 14 in the winter, it's still a big city, and there's an airport? It's like, nope, probably don't want to live there because, the temperature or whatever. But I didn't tell it, like, what is more important, which of the features is more important, right? It kind of figured it out on its own if you look at the weights. So that's an example of this algorithm. So putting it all together, how to finish building this tool, basically, once I have the model trained, I just load it from database or whatever. These are basically the weights we calculated. I have some hard-coded rules to skip things that I shouldn't even try to run the algorithm on. Like, I think in my case it was some weird truncated retweets. If my friends tweet at me, I don't want to really run through the algorithm. That's clear that I want to see those all the time. Tweets mentioning my friends and things like that. So we just skip those. And then we do the classification into good and bad. I think my remote cut out here. Let's see. So, and how do you do prediction? It's the same hypothesis function. Like, it's the same function with the dot product and everything, but now instead of feeding it the training data, we feed it new data. So we take that and we sort of substitute that in, and you end up with this kind of big looking thing, but It's gives you the output. Like this is the dot product, that's the function, and you calculate it, and it gives you a number between 0 and 1. That gives you the probability that this is in that class that you're trying to determine. So in my example is if it's greater than 0.5, I consider it bad, otherwise I consider it good. But I can adjust that threshold. Like in my case, I wanted to be fairly cautious that I don't necessarily end up with a whole lot of false positives and I like block the person and never see their tweets again, because what if it was like somebody that actually had a valid tweet but I just misclassified them. So the threshold is figuring out what the threshold should be is a little bit of an art. But then the general flow is that for each tweet that comes in, I run the same feature extractors to extract the features, giving my array of features. Then I run the model and act on the result. And so if it determines that it's a bad tweet, it blocks the user through the Twitter API. And I never see from them again and I don't see that tweet either. And the kind of cool thing about this approach is that I don't need to have a proxy that's sitting in front of Twitter and I connect with a proxy from all my clients. Like all my client devices, the phone and the web, they work with Twitter directly. It's just the user is blocked and kind of never appears in my reply stream anymore. So some of the lessons learned from this. Twitter API is a big pain in the ass. Who here has worked with Twitter API, especially a streaming one? Do you like it? Yeah. I can't, forget the documentation, which is okay. The number of times that I ran into things that were undocumented, like the error codes, they weren't really explained, or just random, bad things happening is too high to mention. I really wish they concentrate a little more on their API rather than pissing off developers. Blocking is the only option in my case, and it's pretty final. Like, if I misclassify somebody and I block them, like I said, I'll never see them trying to say, hey, why did you block me, and so on, right? Like, that's the only way for them to get a hold of me is to have somebody else contact me or email me or whatever, right? I also found out that the streaming API delivery is incomplete. There would be cases where I would go into my reply stream on Twitter website, and I would see a tweet there that was not delivered to the streaming API. Like, I don't know why that happens. It's just another example of Twitter being very inconsistent. I judge the tool to be about 80% effective. I'm still going to keep working on it, but it's already a big help. I also learned that PHP sucks at mathy stuff. It doesn't really have tools for doing anything besides, I don't know, simple arithmetic stuff and maybe, I don't know, square roots and exponents and things like that. But you really want some of that to do really cool algorithms. So some of the next steps that I can take with this, I can do more of a real-time feedback loop. So as build something where as the new tweets come in and I'm like, oh, this actually is a bad one, but you missed it. I would just click a button somewhere and it would go and add it to the model and, update the weights and so on. So some sort of real-time feedback. I could look at more features to see what else might be fed into the model. I could do some grammar analysis to for some tweets that ends up being that it's English and it's actually valid English, but people say stuff like I'm at a bar, which I don't understand why they do that, but I could try to determine those cases and add it to the hard-coded rules. Another thing to look at is a different learning algorithm called support vector machines, which deals much better with the biased cases. So I wouldn't have to do that synthetic oversampling that much. I can use, and there's actually a PHP extension called SVM that I think Ian wrote. So it could be another thing to look at. Twitter recently released something called Clockwork Raven. Have you heard of that? It's like a library and an app to help you submit data to Mechanical Turk and work with that in an easier way. So that could be useful if I wanted to redo that manual classification, like if I ever need to retrain them and relabel the model, I could use that and have somebody actually sit there and say, this is good, this is bad, rather than me doing that for a bunch of hours. Other minimization algorithms, like BFGS or conjugate gradient. Gradient descent is simple, but it has, you know, like I said, certain issues. It doesn't give you the global minimum. You have to figure out what the learning rate should be. And these algorithms are more complex, but they don't suffer from that. And I really want something like, Python has this thing called scikit-learn, which is a whole big library that has awesome machine learning stuff, so you can write actual apps and tools based on that. And I wish there was something like that in PECL for PHP. So some of the tools used are MongoDB, I already mentioned, the text language detect library in pair. The underlined one's a link, so if you see the slides later, just click on them and go there. English vocabulary corpus, which has like 1 million English words, and I use that to clean up some of the language detection stuff, as you can see in the slide notes later. So is parts of speech tagging system. SPL fixed array is part of the SPL extension, and it basically gives you a simpler and more memory efficient arrays rather than what the PHP has, which are not really arrays, they're like ordered maps basically, because you can throw anything in them. And this is just like, okay, I'm going to have 10 entries of numbers and that's it. And it helps you with some speed and memory efficiency. Firehose, that's the tool library that hooks into Twitter streaming API. And I actually used Python's scikit-learn to validate the results, which was useful. And the link to the code sample as well. So I think we still have like time for a few questions if you have them. Anybody?
Is it worth it having a short Twitter name?
Yes. It is worth to have a short Twitter name. Did you see the fame, the followers, the fortune and stuff like that? No. It's worth it. Even just as a conversation starter, if nothing else. Who else? Okay, in the red. What? Mike?
How many users have you banned?
I'm sorry, can you repeat that?
How many people have you banned on Twitter?
How many people did I ban? So for each block tweet, I also save it to the database, just because in case I wanted to run some analysis on later or whatever. And I think it's in the hundreds of thousands now. I don't know if I'm the #1 blocker on Twitter or not, but I might be. Yeah, behind.
How does it compare in terms of accuracy and efficiency to classification neural network?
How does it compare?
Like a Bayesian classification system. How does it compare in terms of accuracy?
Well, it's a very simple algorithm, right? And I kind of used it because I sort of thought I might give this talk, and it'd be easier to explain than something like supported vector machines, or so it could be better, is what I'm saying. But this way, it's I think a little more transparent about what's going on. Yeah.
Yeah.
Have you heard back from Twitter? It seems like the type of thing they should be doing for us. Do you get any feedback or interaction with Twitter about that?
Have I had any feedback from Twitter about this or interaction with them? Not really. I mean, I know some people who work at Twitter, like somebody on their API team and so on, and I complained about this stuff, but there's not much that they can actually do, right? I mean, they're not going to run something like this and automatically block people for me. So it's sort of, I mean, it comes with the territory apparently. And if you think Twitter is just what you see and they sort of your reply stream, like there's a whole big dark Twitter out there that's just horrible stuff. You know, as I was like looking at, if you just look at the streaming API and there's a sampling one that just shows you like 10% of what's actually going into Twitter, and you just look at it for a while, you'll be horrified. Like, just the abuses of the language, for example, that go on. So it comes with territory, and that's why I kind of had to take this into my own hands and do stuff. Feedback about the actual Twitter API sucking, that's nothing new. You know, I don't know if they're motivated to fix that or not necessarily. Anybody else? Yeah.
This is working? Yeah. I was just curious as to how much you knew about the tools and the maths behind all this stuff before you kind of inherited AA, or did you just really hate spam and have to learn it all?
How much of this did I learn before?
Yeah.
I've always been sort of interested in kind of machine learning and in artificial intelligence, but I haven't. I hadn't had a motivation to apply it to something like a real project until this. But there are a lot of different ways you can use machine learning, even for simpler stuff. And I think Google has a new thing where you can, basically it's a predictor system. You feed it training data, it figures out the model parameters, and then you feed it new stuff and gives you the output through an API. I haven't taken a look at that, but that might be another thing for me to consider, you know, maybe because then I don't have to really do anything. I let Google do all the cool algorithmic stuff. But on the other hand, like, it's just kind of neat that I just, you know, wrote this myself and it's actually working. Yeah. Just go ahead.
Actually, you're doing
Sorry.
You're doing language processing. How do you tackle the problem of stop words and stemming? So, for example, you have emoticons, you have smileys.
So the question is the language detection. How do you deal with stemming and stop words and all that stuff? There's a whole slide that I omitted, but I'll include in the one as I upload, where when it gives you back data and says this is English, it may not be English, for example, right? So I ran through a whole number of other steps to clean it up, where like I check whether it's English vocabulary or not, first of all. If it's not there, then I run parts of speech analysis on it. And if it's one of three classes, like if it's a third person singular or something, or a verb in the past tense, then I do stemming on it, and then I check if it's an English vocabulary again. And sorry? Not SoundX, no. There's a Porter stemming algorithm. I think there's a library for that in PHP too, which works pretty well for that. But yeah, language detection is a messy thing. Thanks a lot for coming to the talk. You've been super audience. Thanks for the questions as well. If you could go to this joined in link later on and leave your feedback. The slides will be linked from there as well in about an hour or so, or within an hour. And if you want to chat about this stuff again, I'm going to be all night here at the social and so on. So just come and chat. Thanks a lot.